So the energy correction ended up not being too complicated. The wave function correction is a little bit more involved, but let's go ahead and look at it. So if we're looking at our wave function, because often we want to know what are the probability distributions and things that we can learn from wave functions, we've written that our wave function, and again we're looking just at the first order, is our zero order wave function, which we presumably know, and we would like to know what's the correction, right? So the question is, how do we find this? Well, so when we're looking at wave functions, we're generally looking at a whole set of wave functions. And so our psi 0 is usually has an n, some quantum number. And so this is a set of wave functions for our system. And this is for our known system that we're using as sort of the basis for our perturbation theory. And what we do is we use these to define our first order correction. And so our wave function n, right, so writing this out, we actually have, this will be for a specific quantum number, of our system, is going to be equal to the zero order wave function, and we'll have some linear combination of all the other wave functions that make up zero order wave functions that make up our set of systems. And here, where m does not equal n, right? So these are all the other wave functions. For example, if we have the particle in a box, to put this in specific terms, right, we have a set of wave functions psi n, square root of 2 over a, sine n pi x over a. And say we were doing a perturbation theory problem with this, and we wanted to find the correction to the n equals 1 wave function. So our n equals 1 wave function, the psi 1, 0, would be our just regular wave function, sine pi x over a. And then we'd add a little bit of our other wave functions that make up our system. So we'd have some coefficient a2 times the psi 2 wave function for particle in a box, and then a3 plus psi 3, times psi 3. And we would add all the other possible parameters. Now the question is, how do we find these coefficients? And this is given, we won't go through the derivation of this, we'll just look at the result. The coefficients are given by this equation. Am is equal to an integral of psi m star, psi m 0, with the perturbation h1, psi n 0 d tau. So m represents, and let me be clear here, m is the correcting wave function. This is not the wave function that we are finding the correction to. These are the ones we're adding to it. So let's say the correcting wave function, and there'll be a whole set of these, right? This isn't just going to be one. Whereas n here is equal to the wave function being corrected. In the previous example I gave, n will always be equal to 1, whereas m will change from 2 to 3 to 4 to 5 to 6 to all the other ones. Okay, so we have that integral divided by the difference in the zero order energies of our wave functions here. And again, m cannot equal n. So these coefficients tell us how much of our other known wave functions we add to find the perturbation. And again, this contribution could have, up to infinite terms, and we usually have to cut it off at some point, right? We can't generally find these infinite sums. So if we summarize this in one equation, our wave function is equal to our zero order wave function plus the sum over m of our other wave functions. So psi 0 star m h1 psi n 0, these should have n's on them, d tau over en 0 minus em 0 times psi m0. Right, so we have all these, this is just combining the coefficients into this equation. In practice, because of this term on the bottom that I'll circle here, this difference in energies, only those wave functions, the m wave functions, that are close in energy to the one we're correcting will have significant coefficients. So because this difference in energy matters. So the closer the energies are, the larger these coefficients will be. So usually, so I guess we'll say generally, only psi m0 that are close in energy will matter. So even though this could be an infinite sum, the largest coefficients are for those wave functions that are closest to the one we're correcting.